Okay, guys. Okay. Free radicals. We talked about the superoxide anion. So we had a question about this reaction right here, the free radicals. What happens with free radicals? So we know that we generate, as a byproduct of metabolism, metabolic waste and also reactive oxidative species. Those reactive oxidative species are very dangerous because they damage the tissue, leading to the breakage of the integrity of the cell membrane and damaging very important protein channels and so on. So what is the major example of this free radical is the generation of the superoxide ion, O-2. So you need to know the superoxide dismutase, SOD, S-O-D. The superoxide dismutase is an enzyme. What does it do? It's an antioxidant enzyme. It's an antioxidant enzyme that what it does is it converts this really dangerous superoxide anion. So you know that O2 is oxygen. O2 minus is what? O2 is oxygen. O2 minus, what's the name of O2 minus? Superoxide anion. Superoxide anion. Okay, so superoxide dismutase, it will mute it. It will mute this superoxide anion and convert superoxide anion into two things: oxygen that we can breathe and hydrogen peroxide that is very similar to water. Selenium, vitamin E, vitamin C, and carotenoids from your carrots are also examples of antioxidants that are obtained from the diet. Okay, so atoms combine. Atoms combine with. So now let's talk about molecules and chemical bonds. So atoms can combine to form molecules. So a molecule is a particle that is composed of two or more atoms and united by a chemical bond. So we have one or two atoms, like sodium chloride. Is sodium chloride an example of a molecule? Yes, because it combines two or more atoms. So what's a compound? A compound is a molecule that is composed of two or more different elements. A compound is a molecule that is composed of two or more different elements. It can be represented by a molecular formula, which identifies the constituent elements and how many atoms of each are present. So that molecular formula tells me when I say sodium chloride, NaCl, I know there is sodium, I know there's chloride, I know the weight of sodium, I know the weight of chloride, and I add them both together, they will give me sodium chloride. Also can be represented by a structural formula, which identifies the location of each atom. Now that's interesting because that leads us to stereochemistry. Because isomers, what are isomers? Very important to know what isomers are. Isomers are molecules with identical molecular formula, but they have different arrangements of their atoms. They have identical molecular formula, but they have different arrangement of their atoms. Like here, like ethanol and ethyl ether. So what's the difference between ethanol and ethyl ether? They have the same number of carbons. 1, 2 for ethanol, 1, 2 for ethyl ether. They have the same number of oxygen atoms. 1 oxygen atom for ethyl ether, 1 oxygen atom for ethanol. How many hydrogen does ethanol have? 1, 2, 3, 4, 5, 6. How many hydrogen does ethyl ether have? 1, 2, 3, 4, 5, 6. So they have the exact same number of atoms, but they are structured differently. So now look at the condensed structural formula. So the condensed structural formula is CH3 representing this side, CH2 in the middle, OH to the outside. And the structural formula for ethyl ether is CH3 on both sides and in the middle is O. But the molecular formula is the same. So the molecular formula is how many molecules that do I have. But the condensed structural formula is different because I arrange them differently. So I have the number 1, 2, 3, 4, 5. If I put them in order, it's different than I could put 2, then 1, then it's like a phone number. 718-314. I can change it to 718-413. Then I can make alterations. So isomers, they have the same molecular formula, but different structural formula. These atoms are the same, but they are connected to each other differently. So the molecular weight of a compound is the sum of the atomic weights of its atoms. Is the sum of its atomic weights of its atoms. So now let's look. Carbon. So for example, if I look at glucose, it's very cool to remember what is the glucose number. Glucose is C6H12O6. C6 meaning that it has 6 carbon atoms and each carbon is worth 12. How did I know? How did I know that each carbon is worth 12? Is when I go to the periodic table. Let me go to the periodic table and pull up my periodic table. So in the periodic table, I have, let's look at carbon. Let us now look at carbon. Carbon has, it is not showing me. So let's look at carbon. Carbon has how much? 12 atomic mass units. You see? Carbon has 12 atomic mass units. So I have 6 of them. So I multiply, that's a typo, that's a typo. So 6 carbon atoms multiplied by 12 is 72. And I have 12 hydrogen. Hydrogen has what is the molecular weight for hydrogen? Is 1. And 6 oxygen, the molecular weight for oxygen is 16. Then I add all of them together, then the molecular weight of all of glucose is the sum of all of them. That comes out to 180. Okay, now let's talk about the chemical bonds. So the chemical bonds hold the atoms together within a molecule. Chemical bonds hold the atoms together within a molecule, or they attract one molecule to another. So we have ionic bonds. These are attractions of a cation and an anion. The one who has an electric charge, an extra electron, will have a relationship with one that has no electric charge. Okay. So an example is sodium and chloride ions. They bond to form sodium chloride. So relatively easy broken by something more attractive, such as water. So water now, oxygen is so electronegative, will take away sodium from chloride, and it will replace that, okay? Covalent bonds. Covalent bonds are atoms that share one or more pair of electrons. So we have single covalent bonds, we talked about that, a nuclei that share one pair of electrons, and a double covalent bond, and that's a nuclei that share 2 pairs of electrons. So if electrons are shared equally, it's a nonpolar covalent bond. So an example of that would be carbon atoms bonding together. That's a nonpolar covalent bond. But if electrons are shared unequally, so one has more of the electrons in the bond than the other, that is now known as polar covalent bond. So the hydrogen bonding with oxygen and the electrons spend more time by oxygen. So that shows. So let's look at that. This is a single covalent bond. So this is a hydrogen atom and a hydrogen atom with one electron spinning. So both of them will join together, and then I will have two hydrogen atoms that are connected with a single covalent bond. Okay, the double covalent bond. Double covalent bond means that there are two electrons that are shared. So let's look at oxygen bonding to carbon. So here, carbon is sharing two electrons, and oxygen is sharing two electrons, and now they have a bond. Oxygen is sharing two electrons, and carbon is sharing two electrons, and they are having a double bond. So now let's look at nonpolar. So even though both of them are sharing one bond, there will be a polarization. So one is taking more. So let's say two people are sharing a cab. Two people are sharing they're working as taxi. So they go and they rent the car for 24 hours and they pay $200 and they say, okay, I'll take it for 12-hour shift and you take it for 12-hour shift. That's a non-polar bond. But if one takes it for 14 hours and the other one takes it for 10 hours, then that's non-polar because one is taking more. So that's what's happening with oxygen and hydrogen. In oxygen and hydrogen, as we see in water, OH, electrons are being pulled more. They are spending more time with oxygen than they are with hydrogen. So that's a non-polar bond. You see the bubble is bigger around oxygen than hydrogen. But here, the bubble is the same for both. Okay, molecules and chemical bonds. So a hydrogen bond is a weak attraction between a slightly positive hydrogen atom in one molecule and a slightly negative oxygen or nitrogen atom in another molecule. So that's a hydrogen bond. It is not a strong attraction, it is a weak attraction. And you would have a slightly positive hydrogen atom in one molecule who's like, for example, in water. In water, the hydrogen in water is slightly positive. So that hydrogen can now go and bind with a slightly negative oxygen of another compound or a slightly negative oxygen or a slightly negative nitrogen of another compound. So the water molecules are attracted to each other by hydrogen bond. We talked about that. And the large molecules of the DNA and proteins are shaped in part by the formation of the hydrogen bond. So the double helix of our DNA, why does it stay together as double helix? We denature it when you heat up the DNA, it denatures. Also the proteins, when you heat them up, they go from a quaternary structure to a tertiary structure to a secondary structure. Why? Because they were held together by hydrogen bond. This is really important for you to know the significance of the hydrogen bond. You say that these are weak bonds that are used for structural bonding, like in the DNA and in proteins. So these proteins and DNA, when you heat them up, that hydrogen bond allows for the breakage of, the heat would break the hydrogen bond, and then we would reverse that conformational change. We will see now an example. So that shows you water is H2O. You see two H's and one O, but the bond is not similar. So the bubble is really tiny around hydrogen, making hydrogen more electropositive, and is really big around oxygen, making oxygen really electronegative. So now the electronegative is going to have a bond with the electropositive. That's an example of what kind of bonding? Ionic bonding. What kind of bonding is that? That's hydrogen bonding, because you have a weak hydrogen plus bonding to a oxygen minus. Weak hydrogen plus, oxygen minus. Weak hydrogen plus, oxygen minus. So that's hydrogen bonding. And we use that kind of bonding in water when we're solvating, versatile, the water being versatile solvent. So it solvates like that. And also conformational changes and all for DNAs and proteins and so on. Okay, there is another type of chemical bonding, and that is the van der Waals forces. So the van der Waals forces are weak, and they are brief attractions that happen between the neutral atoms. They are weak attractions that take place between the neutral atoms. So fluctuations in electron density within an atom create the polarity for a moment, and they attract adjacent atoms for a very short time. So only 1% as strong as the covalent bond, but play important role in the physiology. So that's also important in protein folding. So remember that van der Waals forces are weak, and they are temporary bonding between they are brief attractions between the neutral atoms. So these are fluctuations in the electron density within an atom, and they create the polarity for a moment. Okay, water and mixtures. So we talked about mixtures, that we have multiple things that retain their properties. So body fluids are complex mixtures of chemicals. And these mixtures consist of substances that are physically blended, but not chemically combined. They are physically blended, but they are not chemically combined. And each substance retains its own chemical properties. So remember in the mixture that it is made up of different substances, and they are joined together, blended together, but they are not chemically combined. And each substance retains, so you can tell which substance is which. So most mixtures in our body consist of chemicals dissolved in or suspended in water. And how much does water constitute in our body? About 50 to 75% of our body weight. So the polar covalent bonds and the V shape give water a set of properties that account for its stability. So it's important for us to know the properties of water. Water is an excellent solvent. It dissolves a lot of different substances. It's a versatile solvent. Cohesion, adhesion, chemical reactivity, thermal stability. Let's look at that. So the properties of water, we have solvency. So the water has the ability to dissolve other chemicals, and water is a universal versatile is a versatile solvent because it dissolves more substances than any other solvent. And it is a metabolic reactions depend on the solvency of water. Hydrophilic substances dissolve in water and are polarized or charged, while hydrophobic substances do not dissolve in water and they are nonpolar or neutral. So like dissolves like, lipids dissolve lipids, and hydrophilic substances dissolve hydrophilic substances. So polar substance dissolves polar substance. So detergent dissolves lipids and fats, while water dissolves the salts and the polar substance that have charge or that are able to dissociate and into electrolytes. So to be soluble in water, a molecule must be polarized or charged. So that's the law. In order to be able to dissolve in water, you have to be charged. You have to be polarized. And the example is attractions to water overpower the ionic bond. So the attractions to the water overpower the ionic bond in the sodium chloride. So water forms hydration spheres around each ion, and the salt dissolves. So the water's negative pole faces the sodium, and its positive pole faces chloride. We talked about that. We described how that's what we did right here. You guys see? We have the chloride is dissolved by the hydrogen plus, while the sodium minus dissolves the while the sodium plus is associating with the oxygen. So oxygen dissolves by making a bond with the most electropositively part of the molecule, and then hydrogen being most electropositive makes a bond with the most electronegative part of the substance we want to dissolve. So NaCl, Cl is minus. So who's going to bind the Cl minus? The O or the H? H, because H is positive. Because why is H positive? Because O is taking all the electrons. Electrons are spending more time around the O, not the H. And who's dissolving the Na plus? The O minus. The O minus, because it has all the electrons, and the Na has no positive charge. The Na has no electrons. So to be soluble in water, a molecule must be polarized or charged. Must be polarized or charged. So an example would be the attractions to water overpower the ionic bond in the sodium chloride. And the water forms hydration spheres around each ion, and the salt would then dissolve. So that shows you that the attractions of water are stronger than ionic bonds. So ionic bonds are temporary. You have a negative and a positive. But the water hydration spheres are stronger. The attractions of water are stronger. So now Na who's positive, that is binding to Cl who's negative, would think that it's better to bind the oxygen with water than to bind the chloride who's minus. It is better for sodium, it is stronger for sodium who's plus to bind oxygen from water who's minus than for sodium who's plus to bind chloride who's minus in salt. So these are the hydration spheres. You see how we make the hydration sphere? O represents oxygen, while so the red represents oxygen and the blue represents hydrogen. And you see that this is minus, that's more electronegative, and this is plus representing more electropositive. So the electropositive stuff is going to be attached to the minus chloride. So the O's, so these H's are electropositive, they're going to bind the chloride minus. While the red is the oxygen, is going to be electronegative, it's going to bind sodium, the electropositive. So now we're continuing. So now we have finished talking about one of the properties of water, being a versatile solvent. It's a versatile or versatile. So how can I remember? Tile, like bathroom tile. Okay. So, all right. So versatile is like a bathroom tile. So I'm never again gonna say versatile. Yeah, okay. Okay. But I'm trying to just say it the right way. Okay. So now I'm gonna remember. It's a versatile because like the bathroom tile. Okay. So now we have finished talking about the water. One of the water's properties being water being a universal versatile solvent, but it has additional properties such as adhesion. So adhesion is the tendency of one substance to cling together to other substances, okay, to around other organs. So cohesion, so the tendency of molecules of the same substance to cling to each other. So the tendency of molecules of the same substance to cling to each other. Water is very cohesive due to its hydrogen bond. So the surface film on the surface of water is due to molecules being held together by surface tension. Okay. Chemical reactivity. So the chemical reactivity is the ability to participate in a chemical reaction. So the water ionizes into H plus and OH minus. So it ionizes other chemicals, acids and salts. It involved in hydrolysis and dehydration synthesis reactions. Okay. Properties of water. So there's thermal stability. Thermal stability is due to high specific heat capacity. We said that. Why do we use water? Where do we really utilize? Where do we really utilize water? We use it for when we sweat. So when we're sweating, we use water's high specific heat capacity to take on the heat of the sun on our behalf. Okay? So we use water as sweat for thermal stability, and that is due to the high heat capacity and the amount of the heat needed to raise the temperature. So what is the specific heat capacity? Specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? I didn't talk about hydrolysis. So when we talk later on about this very important concept known as the amino acids. So the amino acids have alpha carbon. They have alpha carbon. So if I want to make a polymer of amino acids, the amino acids have alpha carbons, and each alpha carbon will have a hydrogen group, a hydrogen group, a hydrogen group, and each hydrogen group will have to its left a amino terminal, an amino terminal, NH3, an amino terminal, NH3, an amino terminal, NH3. Then on its right, you will have a carboxylic terminal, OH. On the right, OH. On the right, OH. And in the bottom, you will have an R group that will make it different. So amino acid 1, amino acid 2, amino acid 3 are different, not because they have different hydrogen, they have the same hydrogen terminal, so they have 4 terminals. Terminal 1, terminal 1, terminal 2, terminal 3, terminal 4, like north, south, east, west. They have the same north, they have the same east, they have the same west. But what's different is the south. The R group is different. The R group is different. So if I want to condense them, what do? I condense them by hydrolysis. 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 So the hydrolysis means minus H2O. I remove water. So how am I going to remove water? I know that this side has NH3. That's what it is. That's an amino terminal, NH3. So what's going to happen is in the NH3 you have N, H here, and H here. So I have an OH on one side and an H on this side. That looks like H2O, doesn't it? So now what I'm going to do is I'm going to remove that. I'm going to take water out. That's why I have minus H2O. I'm going to have H2O out, remove that, and then connect a bond. This bond is known as peptide bond. Peptide bond. So now I made peptide bond. I have condensed them together. That's a condensation reaction. So when I condense for condensation, condensation reaction. When I condense in condensation reaction, what happens is they join together. In condensation reaction, I use hydrolysis. Hydrolysis. For condensation reaction, I use hydrolysis. Yes? So, yeah, synthesis, the same thing. So synthesis is hydrolysis through condensation.
No, but he said dehydration synthesis when you remove the water.
Yeah, that's also true. Dehydration is hydrolysis. Dehydration. Yeah. Dehydration. Oh, I'm sorry. Wow. No, it's dehydration. Dehydration, I'm sorry.
Oh, yeah.
Hydration is when I add the water to something. Very good. Very good, Professor.
Oh, no, you can.
No, your name. You better get that credit, boy.
Nobody's getting no more credit.
No, him, because he's the one that answered.
Okay, so hydration, excellent point. In hydration, so that's dehydration. D, removal. That's why it is minus. Dehydration, removal. Dehydration, I remove water. So I remove water and then they condense. So I condense, synthesis, dehydration. What about the other way around? If I want to, so now that's catabolism or anabolism. When I condense it. Anabolism, good. So anabolism, when I condense them together, anabolism. When I condense them together, anabolism, condensation, synthesis, and dehydration. Okay, now let's go to the opposite. Let's say I want a break. I don't want anabolism. I want catabolism. Catabolism, breakdown. And now I'm not having synthesis, I'm having decondensation. I'm having decondensation. And that's definitely going to be hydrolysis. So here, when I perform hydrolysis, I'm going to add water now, plus water. I'm going to give this side an OH, and then I'm going to give this side an H, and then I separate the peptide bond. So now I cleaved it, I catabolized it. But either way, whether I am condensing or decondensing, dehydration or hydrolysis, I am using water. So that's another property of water. Besides water having high specific heat capacity, besides have water being a versatile solvent, besides the water being able to participate in condensation, decondensation, chemical reactions, that shows you the importance of water. So far, what are the three properties of water that make water the substance of life? Number one, it's a versatile solvent. What else? As heat, but it has a high heat capacity. Very good. And what's the third one? Yeah, it has a very high. So when you say it has specific heat capacity, that it has a high specific heat capacity. And then the third one is it participates in chemical reactions like through hydrolysis and dehydration. Excellent. Good job. Okay. Now, mixtures of other substances in water are classified as solutions, colloids, and suspensions. So the solution consists of particles called the solute, and they are mixed with a more abundant substance, usually water, and it is called the solvent. It is called the solvent. So the solute can be gas, solid, or liquid. The solute can be gas, solid, or liquid. Solutions are defined by the following properties. Solutions are defined by the following properties. So a solute particle is under 1 nanometer. The solute particles do not scatter the light, and they will pass through most membranes, and they will not separate on standing. That's very important to understand. Okay? So mixtures of multiple substances in water are classified as solutions, in colloids and suspensions. So now let's go through the difference between a solution, a colloid, and a suspension. So a solution, what is it? See, I got my own keys now. I don't gotta call nobody. Woohoo! Okay. I have so many keys, so many schools. I'm gonna lose everything now. Okay. So we'll pass. So now let's look at the difference between solution, colloid, and suspension. Okay. So we talked about solution. They consist of particles called solute. They are mixed with more abundant substances, usually water, and they're called a solvent. And the solutes can be gas, solid, or liquid. Solutions are defined by the following properties. So the solute particles are under 1 nanometer, and the solute particles do not scatter the light, and they will pass through most substances and will not separate on standing. While colloids in the body are often mixture with proteins and water, and that's how the thyroid hormone is made. It's first a colloid. It has water with proteins, and it's really thick. It's like a gel. So many can change from liquid to gel state within and between the cells. So the colloids are defined by the following physical properties. So the particles range from 1 to 100 nanometer in size, and they scatter the light and are usually cloudy, and particles too large to pass through the semi-permeable membrane, and the particles remain permanently mixed with the solvent when the mixture stands. Okay, suspension. So suspension is defined by the following physical properties. It is a particle that exceeds 100 nanometer, and it is too large to penetrate selectively permeable membranes. It is cloudy or opaque in appearance, and it separates on standing. So that shows you blood cells and blood plasma. So the examples really reveal everything. So a solution is like water. It always has water, usually water. It has water with salt. That's an example of a solution. That's not a colloid. That is not a suspension. But then when you have a colloid, the colloid is usually water and protein. Water with protein. A suspension is when you have blood cells and blood plasma. An emulsion is a suspension of one liquid in another. So now you don't have blood vessels, blood cells, and blood plasma. Now you have oil and vinegar. Like for example, like when you add oil to vinegars in the salad dressing, or fat in breast milk. So that shows us a solution, a colloid, and a suspension. That's a solution. So the particles are really small in a solution with water. So in solution, most of the time, we deal with water. While a colloid, it has water usually with a protein. But a suspension, you have really thick red blood cells with that are dissolved in it has really big particles, too large to penetrate the selectively permeable membranes. And that's like red blood cells in blood plasma right here. And also that's an example of a suspension. So is blood a suspension or blood? Is it a suspension? Yes, because it has red blood cells that are dissolved in plasma. And an emulsion is when you have one liquid. So now you don't have red blood cells, you have liquids dissolving in other liquids like oil and vinegar, or fat in the breast milk, or yeah, fat. So you have nonpolar dissolving in the nonpolar breast milk. You have oil dissolved in vinegar. That's an emulsion. So an emulsion, you will have like water and oil. What is water and oil an example of? Water and oil. That's an emulsion. So both cannot dissolve in each other. So you would have a suspend. So you'd have like an emulsion. That's an emulsion. Now we're getting to talk about acids and bases, which is one of the homeostatic variables we need to repair. So when we are dealing with acids and bases, we said earlier that an acid is a proton donor. So acids are substances that can be, substances can be acids or bases depending on their tendency to release or bind hydrogen ions. So an acid is a proton donor and it releases hydrogen proton ions in the water, while a base is a proton acceptor and it accepts the hydrogen protons. Or so a base can do two things. It can accept hydrogen proton or it can donate hydroxyl ions, OH. So a base can accept hydrogen proton or donate hydroxyl ion. But an acid only donates hydrogen proton. So you must really know this one. This one is really important. You must really understand that an acid is a substance that increases the concentration of hydrogen protons. And if the hydrogen protons increase, what happens to the pH? The pH decreases. Okay? Now, the base. The base is increasing hydroxyl ion concentration. And when it increases hydroxyl ion concentration, the pH is going to go up. But the problem is for homeostasis, we have a fixed range. The maximum is 7.45 and the minimum is 7.35. You need to know this one. You need to know the physiological homeostatic range for pH between 7.35 to 7.45. If you go below 7.35, that is known as acidosis. And if you go above 7.45, that is known as alkalosis. Good. Alkalosis. So if we go up, we must come down. That's known as negative feedback. Negative feedback. So if we go up, we must come down. Or if we go down in acidosis, we must return back up. That's an example of positive or negative feedback. So when you repair things by doing the opposite, that is negative feedback. If you repair things by doing the opposite, negative feedback. If you intensify, then that's an example of positive feedback. So you must know this relationship well. That if hydrogen, so acid, so I can ask you on the exam, an acid is a substance that increase hydrogen proton, increase the pH. False. Increase hydrogen proton, decrease the pH. True. A base is a substance that accepts hydrogen proton. True. Accept OH minus. False, because it donates OH minus. It makes the hydrogen concentration go down. False. It makes hydrogen proton hydroxyl ion. This hydroxyl ion. It makes hydroxyl ion go up. And here it makes the hydrogen proton go down. Hydrogen proton concentration go up, the acid. So the base makes the hydroxyl concentration go up, and that leads to the pH going up. So you must really have a good understanding of the pH. So substances can be acids or bases, depending on their tendency to release or bind hydrogen ions. So an acid is a proton donor that releases hydrogen proton ions in water. And a base is a proton acceptor. It accepts hydrogen proton ions or releases hydroxyl ions in water. Acidity is measured by the pH scale. So we talked about that. So 7 is right in the middle. So that makes 7 neutral pH. And the pH of less than 7 is acidic. So if the pH is less than 7, does that mean the hydrogen proton concentration is more or less? Hydrogen proton concentration, when we have a pH less than 7, does that mean hydrogen proton concentration more than OH or less than OH? More than OH. When you have the pH at 7, do you have more hydrogen proton or more hydroxyl ion? They are equal. Very good. And when the pH is greater than 7 or basic, that means the hydroxyl ions are more than the hydrogen proton, or the hydrogen proton is less than hydroxyl ions. So maintaining normal pH, maybe a slightly basic, just a little basic, because you know neutral is 7. So our pH is not 7, is not neutral. Our pH is slightly basic, yeah, because it's 7.35. We said 7 is the middle. 7 is neutral. 7 is neutral. We're not at 7. We are between 7.35 to 7.45. That's basic. That's why when you drink acidic stuff, is not healthy for you, because it's gonna make your blood acidity go up. It's gonna make your pH go down. So maintaining normal, slightly basic pH of the blood is crucial for physiological function. So buffers are chemical solutions that resist change in the pH. So the pH is the negative logarithm of hydrogen in molarity. So the pH is minus the log of H plus. So an example, if the hydrogen proton concentration is 10 to the power of minus 3, when I take negative log of that, I will make the 3 positive. So now it will become 3. So you need to know this relationship. What is the pH? The pH is negative the log of negative logarithm of hydrogen. So if the hydrogen proton concentration is 10 to the power of negative 3, then the pH is minus the log of 10 to the power of negative 3. That comes to 3. So now let's reverse. Let's calculate now. If a pH is 7.35, if a pH is 7.35, that means the 7.35 is the same thing as negative the log of 10 to the power of, so it has minus 3, so that's gonna be minus okay, so that means negative log of 10 to the power of this number. When we take it, that will give us the pH. So pH is negative log of the hydrogen concentration. Remember that the pH, this is so important. The pH equals negative log of who? Who? Hydrogen what? Not hydrogen ion, hydrogen proton concentration. How much do I have? Negative log of that will give me the pH. I'm sorry? Okay. So the pH is negative log the concentration. How much hydrogen proton concentration do you have? When I calculate that, when I calculate it, millimoles, if I take negative log of that will give me the pH. Just, this is an algorithm. So we don't have to go into the details of the math of what an algorithm is, but we need to know that we relate the pH to the negative log of the hydrogen proton. Okay, concentration, not the OH. So on the exam, the question will be true or false. The pH equals negative log of the OH. True or false? That's false. Okay. So the pH is negative log the hydrogen proton. Okay, concentration. That's the pH. Yes. Okay. Okay. You wanna break? Okay, so take a break now.